Can you answer the question?
Yeah, sure.
So, like, you talked about using alkyl sulfate. You gave us an example where we had. We were trying to figure out where the hydrochloric acid comes from in your example.
What lecture is that? Hey, what's up?
Can I see an extension for the moment?
Yeah, just email me and I'll give you one. Yeah.
We were talking about transformation of secondary alcohols to alkene without rearrangement, and then we talked about using an alkyl sulfate. Oh, I just reversed it.
You mean like this?
No. Yeah.
Okay. So the alcohol will attack this, right? And kick off chlorine, SN2, whatever. And then pyridine here will attack the H. Gives you this. And the pyridine. CL minus.
What is it, the CL minus? Actually, if we file and figure out the.
So is it the CL takes the
Eh?
hydrogen again, or is it just that it attaches to the? How does that work?
So, question is, why doesn't chlorine attack and just displace this group? And the reason it's tied up with the pyridine is there is more attracted to the positive charge, so that's why it's trapped. Yeah.
Okay, so that's what the HCl is.
Yeah. So this is where the HCl comes from. The pyridine kind of mops it up.
Okay.
Yeah. All right. Wraps up.
Thank you.
You're welcome. All right, guys. Let's focus in here. All right. So quiz during lab. When you set up the distillation, it'll have to run. Not sure how long it's going to run. So we'll take the quiz then. Okay. It'll be a while because our hot plates aren't the best. All right. So one thing I want to bring your attention to is last week, kind of made an error. On Tuesday, made an error on naming these E and Z. So I want to go over that again. All right. So when you're picking priorities, you look at both carbon atoms. Okay. So you don't go across the carbon atoms. You look at the individual alkene carbons. Okay. So you look at this carbon here, and you look at the two groups. So you're comparing these two groups here, all right, and picking which one has higher priority. And the one we picked was the one on top, so that has higher priority. And then you're comparing these two groups, which one has higher priority versus lower priority. So we kind of named them wrong last time, or I named them wrong, okay? But you look at the sides, okay? And then you're like, okay, well, my higher priority is right here, and my other higher priority is right here. So they're kind of diagonal from each other. So that's trans or E-alkene. So we call that an E-alkene, okay? And we also named it incorrectly, so I want you to change that. So we want to change this name to this. I'm going to write in blue, so you can see my blue numbering here. E-3-ethyl. So this is the 3 position, 3-ethyl. Sorry about that. 2,4-dimethyl. So if we name it this way, we have potentially 4 substituents So it's better to name it this way. And then driheptene. All right, so this was like last lecture. It was like we just scrolled down a bit, like the second page. We scrolled down there. Okay, so I just want to clarify that. So now, now that we named that alkene, how about we name this one up here? This one also has. So this one right here, this one can also be named as E or Z. So I don't know if you go over that one. All right. So let's look at the two priorities here. So at this carbon atom, we have an H and this branch group here. So which one's higher priority? Is it the H over here? Oops, does it work? Damn, it doesn't work. Not working. All right, does this H have higher priority? Or is it this, this long chain here? Yeah, so this one has higher priority. Okay, and then you look at the other carbon atom. This carbon atom right here. Which one will have higher priority there? Isopropyl or the methyl? Yep, this group right here. So this has the higher group. So this is also, they're on opposite sides of each other, right? So that's also an E alkene. Okay, if they're on the same side of the double bond, they'll be a Z alkene. Okay, so I just want to clarify that a little bit. All right, any questions about naming from last time? Are we okay? All right. So we went over alkenes last time. So just remember the double bond is usually weaker. So I'll give you a little example here. All right. So the double bond right here. So let's just circle this double bond right here. This double bond is 65 kcals. And the single bond, so this is the double bond. Let me just put that in parentheses. Double bond. Double/pi bond. All right. So here, I'm going to point to the sigma bond. Here's the sigma bond. That one is actually a little bit stronger, and that's 108 kcals per mole. Okay? So the double bond is a combination of the single bond and the double bond. So that's why it's typically stronger than a carbon-carbon single bond. And given this weakness of the double bond, the pi bond, it'll tell us that that's the bond that's primarily going to react. In much of the reactions, we'll see. Okay? All right. So that's what I wanted to kind of elaborate on alkenes. Okay? So we talked about polarity. So now we're going to talk about hydrogenation. Are any questions about the strengths of bonds there? So that's why like trans fats and cis fats, they can be converted quite readily because the energy to break them is not very high. So they can actually break quite easily in the body. Okay. So we talked about melting points. Don't worry about that too much here. And then we kind of ended last time on acidity. So don't forget acidity of compounds. Okay. So let's go to, here's the new stuff today. All right, so let's talk about stability of alkenes. All right, so we answered the question, which of the following compounds is most stable? All right. So we're going to have, oops, sorry, I even, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. I think I made a mistake. All right, sorry guys, erase that bond. Let's put the double bond right here. So you have three kinds of isomeric alkenes. They all have the same chemical formula, but the double bond placement is all different. Okay, so how do we determine something's more stable? Is we burn it. Oh, I won't say burn it. We hydrogenate it with hydrogen and see how much energy is released. All right. So here we measure the heat of hydrogenation. Heat of hydrogenation. Okay. All right. So what we do here, this is a new reaction. We'll see how it works later on. You have hydrogen. And you have a very expensive catalyst, palladium on carbon. It doesn't look very different. It doesn't look very different from charcoal. Okay, so you can't really see the palladium, but it's there. All right, so what this does, it adds hydrogen across the double bond, so you saturate the alkene to get the alkane. And you'll notice here that you'll get the same product no matter where the double bond is. But here, the delta H of reaction is much different for each of them. So we have kcals per mole. All right, so for this one, since the starting alkene was different, you're going to get different amounts of energies. Okay. So the less negative the number, the more stable the alkene was because it didn't release that much heat. All right. So if you don't release that much heat, you're pretty much a stable compound. All right. So in this case, which one out of all these three, which one is the most stable alkene? The last one, because it released the least amount of heat, right? So it didn't have, it was pretty stable to begin with, all right? So we notice here that the least substituted alkene is the least stable, and we'll see that trend with the other alkenes. And we see here that cis alkenes are less stable than trans alkenes, and you could kind of attribute that to steric hindrance. Remember we talked about if two carbon atoms are too close, they'll be less stable. Okay. But now let's kind of just rank all the possible substitution patterns here. So I'm going to draw a graph. So let's draw a graph. All right. So here's my negative delta H, and I'm going to give it put high HYD to indicate hydrogenation. So right in the middle, let's put this as dirty because our ranges here are not going to be that very wide. So 30, 35, and here let's put 25 right here. All right. So if we have no R groups, your alkene is going to be right here. All right, so this will be around 32.6. Okay, so 32.6 right there. All right, well, we already did one of them. One was mono-substituted, so only one R group on the alkene. So that's around 30.1 here. So let's put it closer to 30 right here, 30.1. Okay, then we have the cis alkene. All right, 28.4. All right. Yeah, sorry, some of these values are just slightly different. I think because I referenced multiple sources. That's why they're a little bit different. But they're still pretty close, so not a big deal. All right, so you see the more substituted and the more, in terms of di-substituted, the trans isomer is more stable. But now we get to the even more stable, tri-substituted alkene. So this would be 26.7. And lastly, you have one last one right here. So this is not drawn to scale, but 26.4 is for our tetrasubstituted alkene. Okay. All right. So which one of these alkenes is the most stable? Non-substituted, monosubstituted, cis disubstituted, trans disubstituted, tri-substituted, or tetrasubstituted alkene? Yeah, we can see right there, right? It's the lowest one, so it's going to be the most stable. So let's just annotate that right here. Most stable, lowest energy. All right, so the reason why it's the most stable is because we talked about before, it has to do with hyperconjugation. Okay, so if you remember hyperconjugation, like alkenes, they have a p orbital, and the carbon groups can kind of align along the p orbital and stabilize the alkene. So the more carbon groups you have, the more stable it is. Okay, are any questions on this graph? You don't have to memorize these numbers, just be familiar with the trend. More substitute alkene is the most stable. And if you're forming alkenes in a reaction and the reaction is being heated, you would want to draw the more substituted alkene as your potential product, like we showed when we did E2 and E1. All right. So let's comment now on the trend. So we should kind of take note of this trend here. All right. So here's the order of increasing stability of alkenes. All right, so we got CH2. CH2 is the lowest. So less than RCH. CH2 less than R2C. Okay. And this is about equal to a cis alkene. So R cis alkene R. And cis alkene is less stable than a trans alkene, which would look like this. Okay. That is less stable than a tri-substituted alkene. All right, and then the most stable one is when you have the tetrasubstituted alkene right here. All right, so we kind of just mapped out what that graph was telling us. Okay, so any questions about the stability, like why more substituted is stable? Any questions? So that's the trend we see here. All right. Okay. All right. Now, what about alkenes and rings? Let's talk about the stability of alkenes in rings. So here's the order of increasing stability of cycloalkenes. All right. So cycloalkenes, they also form in rings pretty often. So here's the trend here. 7-member ring or smaller. You primarily only get the cis isomer. So cis isomer is stable. So for example, here's a cycloheptane. You see here the bonds around the alkene. They are pretty much only going in the same direction, so they're not trans. So you don't get any stable ones for trans. All right. You have an 8-member ring. So an 8-member ring. Cis is more stable than trans. So for example, we have a cyclooctane here. So this will be the cis form. So cis cyclooctane. All right, that's more stable than the trans one. So the trans one looks a little funky. So let's just draw this really quick. All right, so I'm going to draw the double bond. It's coming behind this bond. Sorry, let's just draw like this. So you get this kind of like, remember that twist boat? Kind of this twist boat structure with the trans isomers. So you can see right away that it's probably not going to be very stable because the bonds are kind of overlapping here. So this is trans cyclooctane. All right. So for 8-membered rings, cis is preferred, and then any other rings below 8, they're pretty much, the cis isomer is the only one that forms. There can't be a trans because it's too unstable. And then you have bigger ring sizes, 9 through 12. So the ring size is there. Cis and trans are equally stable. All right, so let's do a few examples. So here, all right, we're going to draw a few rings here. So here is cis cyclododecane. Sorry, cyclodecane, not dodecane. Well, no, it is dodecene. Dodecene. All right, so that's the cis one. Then you have the trans one. So trans will look something like this. See, we have a trans double bond there. That's why it's called trans. So cis, then trans. So this one will be trans cyclododecene. Like that. All right. So you see here, the bigger the ring size, the more you can accommodate an alkene in there. All right. And then eventually, the larger rings, you're going to get trans alkenes are more stable than cis. All right. So if we're anything larger than 12, so larger cycloalkenes, we get the trans is more stable than cis. Like that. Okay. All right. Are any questions on these cis and trans isomers? All right. Okay. Now let's talk about how we make alkenes. So we kind of seen how to make alkenes in a few examples. Sorry. All right. So how do we make alkenes? So we saw making alkenes, right, in SN2 reactions. But now they were kind of like a byproduct or like something we didn't desire. So let's talk about how we make alkenes on a whole. So first we have bimolecular elimination. All right, E2. All right. So remember we have our H. And then we have our leaving group, 1 carbon away. So it has to be anti 2DH or else it can't form. All right, so our base here will come around and attack the H, kick off the leaving group. Sorry, this should be the leaving group. And then we will get our alkene. So we get the base, the leaving group, right here. And then we get our alkene. So R C double bond R prime. So it's server specific. That's why the R groups kind of stay in their relative positions and they don't change positions here. All right. So the best leaving groups we have, so L here, what are our typical leaving groups? They can be sulfonates, so something like tosylate, SO3 minus. Oh, yeah, this is tosylate. Okay. So R, SO3 minus, they are typically better leaving groups because of their acidity. And greater than iodine, bromine. And chlorine's the worst, but still pretty good. Okay? All right. Well, our bases can be 2 different groups, right? 2 different classes, unhindered bases. And then we have hindered bases. All right, our unhindered bases are going to be edoxide or like hydroxide. So any form of alkoxides or hydroxides, they'll be unhindered bases. Okay? And then our hindered bases, they'll be substituted at the oxygen atom. So O minus right here. And then the other one is LDA. The 2 common ones are LDA, is this guy. Lithium plus. Okay? And then the other counter ions, they can be sodium, potassium, doesn't matter as long as they're somewhat water soluble. Okay, let me zoom in there a little bit. Like that. All right. Okay, so the bases, those are our typical bases there. Small ions like oxygen and nitrogen. Okay. All right. So now that we have this here, let's talk about the E2 reaction in a little more detail. Okay? How they form from alkene, how they form alkenes. All right. So the E2 reaction is, number one, regioselective. What that means, it's regiospecific. So it prefers to attack on one side of, so one alkene will form predominantly. The alkene might form on this side or this side, okay? So it's regiospecific. So we can control the regioselectivity. And then it's also stereospecific. It only occurs in one isomer, in one conformation, okay? So it depends on the relative arrangement of groups. All right, so another word we could say here is stereoselective. All right, so let's first talk about the regioselectivity. So the regioselectivity, all right, of E2 depends on the base structure. So it depends on the structure of base. All right. So there's two kinds of regioselectivity. One is called, we kind of went over them in passing a little bit in haloalkanes chapter. So one is called Zaitsev's rule. So I don't know, I always spell his name wrong. Zaitsev, or some people spell it like this. I don't know, we can't ask the guy, he's long gone. But early when this reaction was discovered, he's the one who kind of found it first and postulated this rule. He came up with it, okay? So what this says is that base, when you use base to cause elimination reactions, so base-induced elimination reactions, so they generally give the more substituted and this turns out to be the more stable alkene. Okay, so that's one way we can get that kind of alkene. Now, there's another rule that if you use a hindered base, you'll get the least substituted alkene, and that's called Hoffman's rule. So let's just underline both of them. Here's one rule, and then here's the other one. So then we have another guy who came up who observed that if you change the base and make it more hindered or more sterically crowded, you will get the other alkene product. So the product of elimination of an alkyl halide with a hindered base is the less substituted alkene. All right. So we could think about it, right? If the base is too hindered, it probably can't approach an interior hydrogen because there's carbon atoms sticking out like a branch. So it's going to kind of poke it away. All right, so let's show some examples. So we have the same haloalkane. We're going to have bromine here. And say we have a different base, all right? Our base is right here. So you might get a combination of the cis and trans alkenes, all right? So there's no there's going to be some ratio between these two, all right? So this will be Zaitsev's rule. All right, and then you might get some of the less substituted alkene. All right, so this would be Hoffman's product. So depending on what base you use, you're going to get a different product based on in different ratios. All right, so let's do an actual example now. Take the same haloalkane, and we're going to choose our base. All right, let's say our base is sodium ethoxide. All right, so unhindered base, and ethanol is our solvent. We actually get a mixture of the cis and trans alkenes. So unless I tell you to write both alkenes, you're safe if you write just a trans alkene, because that's the most stable. So 82%, unless you can't rotate. That might be a situation if you're in a ring, all right? But on E2, since there's a lot of hydrogens, they can rotate, the groups can rotate, so you get both cis and trans alkanes, okay? But now let's change the base up in a different example. All right, so let's use potassium tert butoxide. So if you use potassium tert butoxide, LDA, or sodium tert butoxide, you'll get the product will be the same. You're going to get the least stable alkene, which is this one, 78%. And the other percent is probably maybe the other isomer or some other byproducts. But you don't have to worry about that, okay? So that's how we get, how we can predominantly favor one alkene over the other. So if you need a terminal alkene, you want to use a hindered base. If you want an internal alkene, you're going to use a not hindered base, like sodium ethoxide. All right, are any questions on that selectivity there? No? Okay. So let's talk about the stereochemistry now. So we talked about the regiochemistry right here. So now let's talk about the stereochemistry. So stereochemistry of E2 reactions. All right. So remember, E2 can occur in two possible geometries.
Okay, Andrew.
Yeah, what's up?
Just curious, you said it found a more stable alkene on the unhindered base.
Which one?
When you're going over the rules.
Oh, right. So if you're using the hindered base, it will favor the least stable alkene, which is the terminal one. And that's because this base is so bulky right here. So it's so bulky that it can't actually access this hydrogen. It's only able to access this hydrogen because of the bulky groups. So they can't approach each other, and that's because it's so sterically hindered. Okay, but so in these conditions, Hoffman favors the least stable product, and then Zaitsev will favor the most stable product. All right. In E1, if you have E1, the base doesn't matter. The base strength doesn't matter. So in E1, if you have like say water as the base, it will always favor the more substituted, and that's because the base is not hindered, so it won't factor in to this scenario. And this is just for E2 because that's when the base strength is important. All right. Okay, so how about this one? So two possible geometries for E2. Remember we said the leaving group can be either anti to the hydrogen. So we have the hydrogen here. And the leaving group on the opposite carbon right there. Or the hydrogen and the leaving group can be syn to each other on the same, they're on the same face. All right, so the leaving group here is right there. All right, but what do you think is the problem when the H and the leaving group are kind of overlapping? Do you remember when we talked about Newman projections? What's wrong with this conformation? Yeah, it's eclipsed, right? So eclipse, you are going to have more energetically unfavorable interactions, right? So this is not preferred. It's higher in energy because of that. All right, so this is called syn peripointer geometry. So syn is because there's no angle of rotation between them. They're kind of eclipsing each other. So this will be energetically less preferred. Okay, so E2 likes to favor when H and L are anti-peripointer. So here we would call this anti-peripointer. Another way to say it is co-pointer, but don't worry, they're anti-peripointer. Okay, so this one is energetically more preferred. So energetically more preferred, and that's because the groups are very far away and apart from each other. All right, so let's look at this in more detail now, using an example, okay? So here's our experimental observation. How do we know this occurs in this form or in this transition state where they have to be anti to each other? So here's our experimental observation. We get this observation based on the position of the R groups and the relative position of the alkene, okay? So let's draw a sawhorse projection. So I'm going to draw a sawhorse projection like this. And then draw the front carbon like this. So it's H. Boom. And then the BR is sticking up. Okay? All right. So we have this conformation or this conformation. Oh, sorry, let's point this one up. All right. So the left one, 2R, 3R. So convince yourself that this is 2R, 3R. You would have to convert this back to a Newman, then do a bond dash drawing, but don't worry too much about that right now. So 2 bromo, 3-methyl pentane. All right, and then you have the other isomer. We're just going to draw the enantiomer because the groups are switched now. So 2s, 3s, 2-bromo, 3-methyl pentane. So it doesn't matter which enantiomer you use, you'll get the same products here. And they all occur through an anti-periplanar transition state. So let's put the base here. We get sodium hydroxide reacting with ethanol, sorry. And then you're going to heat it. So remember, heating a haloalkane with a strong base will give you the alkene product predominantly. So here we get the same product, an alkene, like so. All right, so let's name this alkene together. All right, you have 3 different substituents. So let's decide if it's E or Z. So let's start at this left carbon. Man, they're not showing no more. Maybe it's something happened. All right. Well, what about this carbon right here? Look at the 2 groups attached to that carbon atom. Which one has the higher priority? The H or the methyl group? The methyl. So we have the higher priority right here. Lower right here. How about this carbon now? Oh, good. Yeah, the ethyl group. So higher, lower priority right here. Good. So look at the 2 top highest priorities. They're trans from each other, so this is going to be an E alkene. Good. So this will be E. All right. So how do we name this alkene? How many carbons long is this chain? 5. Good. All right. And then if we number it right, 1, 2, 3, 4, 5. All right. So how do I complete the name here? Let's see. 1, 2, 3, 4, 5. Close. So not ethyl. So maybe let me highlight it a bit. Maybe this. So this is our parent chain right here. So at the 3rd position, we have a what? Yeah, methyl. Good. And then where's the alkene? 2 carbon. And then what's the parent name? Pentene. Yeah, pentene, right? Because it's an alkene, so pentene. Good. All right, so let's show how this forms. So let's draw now the mechanism. All right, so the H here and the bromine have to be trans or anti to each other. And then the other atoms here are going to be like so. All right, so we have a CH3 here. And then we have an ethyl group right here. All right, so let's abbreviate the base. I'm going to write it as C2H5. Oh, but I forgot the oxygen. Sorry, erase that. All right, what arrows am I missing? A little practice here for the quiz. What arrows am I missing?
The hydrogen bond going to the carbon-carbon bond.
Yep, there's one. And remember, we need this alkene, right? So look at this alkene. All right. So maybe drawing the products here will help us a bit. All right. So I've removed the hydrogen, so that's clear in my drawing right here. And I made the double bond. But what else do I have to do in order to get the product on the right? Yes, the bromine has to leave. So draw an arrow to the bromine. All right, so just think, okay, well, my carbon lost a bond, so I need to get more electrons, so double bond. And the easiest group to push out as a leaving group is bromine, so that's why bromine goes there. Okay? So any questions on these arrows? Hopefully the homework got you an idea like how to put those arrows. A little more comfortable there. All right. So let's kind of represent this isomers here, okay? So you see here, if we kind of look at this Fisher projection of the molecule above, we can kind of see that if we have the Br and CH2 group, CH3 group here, if they're on the same side, that's going to be an eclipse conformation. Okay. All right. So this is still 2R, 3R. Sorry, let me just rewrite that. 3R. 2 bromo. 3 methyl pentane. So sometimes writing it in the Fisher projection could help you visualize the stereochemistry as well. Okay? But if we translate this actually looks like this in the Newman projection. Br CH3, okay? But the ethyl group here is very close to the Br, so it's going to be eclipsing the Br group, okay? And then these H's will be eclipsing, and then the methyl groups here will also be eclipsing each other. So you see here, not a very favorable conformation. So what the molecule will do is rotate one of the carbon atoms to the more stable anti-conformation, and that's how the reaction goes forward. So we can actually rotate one of these carbon groups here. So let's just keep the front carbon the same. So the Br group to that carbon is going to be like that. And then we're going to rotate the back carbon 60 degrees to get our more stable staggered conformation. And you see here now the H and bromine are primed to leave. So what happens here is the base will come around and deprotonate that very easily. So C2H5O- will come around and deprotonate this. So this is pointing to, we're just forming a double bond there, okay? And kicking off the bromine right here. All right, so this is still the same molecule, 2R, 3R, 2 bromo, 3 methyl pentane. So in this Newman projection, why is it more stable than the other one we kind of drew before?
No longer eclipsing.
Yeah, no longer eclipsing, right? And the groups, relative to the eclipsing one, the groups are, how apart are they? So the groups are further apart, right? Am I? Oh, yes, thank you. Methyl groups can't just disappear. All right. So if they're further apart, we have less. What kind of interactions are less present? So less steric hindrance. And what's the other kind of interaction when bonds try to rotate past one another? Some kind of strain. Yeah, you got it. Torsional strain. Good. So that's why the anti-conformation, that's why it's stereospecific, because the base and the leaving group are leaving or approaching and leaving together. So the anti-conformation is the most stable. All right, so and then what this gives us is the product. So that's how the mechanism goes there. All right, so there's some conformational analysis we kind of have to consider in chemistry. All right, any questions about the E2 reactions? So I would say be able to predict the products of a E2 reaction and be able to draw the mechanism. So if the hydrogen and the leaving group aren't anti to each other, or kind of trans like this, you'll have to rotate one of them in order to get it to that conformation. Okay, but I most likely won't have you do that. All right, but be able to draw the arrows. All right, let's take a little break there, and then we'll pick up back on some reactions, okay? We'll do some practice first, then we'll talk about preparing alkenes from alcohols, kind of summarize what we learned previously. Might be helpful for the quiz. All right, I'm going to take a break and use the bathroom. Hey, what's up?
I have to share a thing.
Yeah, what's up?
So I was doing this one. It was like practice, right?
Okay.
But the thing was, I was like, okay, now bromine is going to attack this, and this is going to go off, and then we're just going to have that. But I'm looking over here, and then I'm seeing that they're doing the carbocation
Shift, yes.
So how would I know? Like, I feel like I would have done this.
Well, so remember here, it's a secondary position, so most likely a carbocation will form.
So if it's in secondary, it's probably going to be
Yeah, with alcohols, yeah.
With alcohol,
Yeah,
okay.
so think a carbocation will form here, right?
Uh-huh.
Think nearby. If there's a nearby position that if you move one of the bonds, you create a more stable carbocation, so tertiary.
Here. Okay.
Yeah, that's why that bond moved there, and you form a tertiary
All right.
carbocation. That's why.
Thank
Yeah.
you.
Hey, what's up? One on Sunday.
I don't know.
All looking at whoever was missing in their
Yeah, that's
We don't have to show it.
you don't have to.
I think I show it, so mark it.
I don't think so.
Okay, so that's not good. Okay.
Yeah, so
If I was writing on my whiteboard, what I did, so that's like, that's really the wrong.
yeah,
Similar.
very similar. See how we'll just do this now.
So I know
Yeah,
it's not
actually
bad.
just do this.
And I'm like, that's exactly what happens to that.
So good leaving group. Now you do S and T. Whereas this was a bad leaving group.
Oh, okay. So when you didn't write that, I was like,
No, so this is only partial positive charge. This has a full-on positive charge, so it'll just hang around.
I'm still looking. So
Yeah.
this is the one that's
No, this will have to be a separate reaction.
okay, gotcha.
So yeah, the chlorine group is how
else. If
it'll
that's
come
from
from
the
yeah.
That's good though.
It's,
I mean, he, it is. He's kind of like,
Yeah, no problem.
Yeah. Not a specific example, but you know, something similar. So just follow what you have. So see here, this is actually.
I was like, I couldn't, this is, like, some people work, but I was like, free draws.
you know,
Like, you don't, like, in the beginning.
did it right there.
No, remember, if you tap that,
Yeah.
so look at here, water forming, so yeah.
Yeah,
Take
yeah.
that.
Dan wants an appointment, but it's at all. It's not fair and and it's sort of like sacrifices somewhere. My son.
No, I was talking about boss, like,
Up here. You're going for this one?
It's a 6 month.
yeah, before and after. So I'm like,
It's like not sad at all, so it's all.
and I have so much stuff for the exam, so
Okay, so look right
so I
here.
can prep for that.
Wait, so this shows you what it should be?
Yeah.
But I.
Yeah, so you can draw the arrow.
Yeah.
The water is less, so you can draw one
I'm on.
of the water molecule.
Just do a master's program and have to take a second part. I got
So yeah, so you draw. No, so add arrow.
all those ways
You're
for
breaking this
rotary that
ball.
keeps her away
Yeah.
from watching them on it.
It's just like,
Bouncing
it's
back.
like, when I just found out, like.
And then, now, yeah, and then you have two water molecules. One.
Yeah.
There you go.
Like, I
And now
think
look
like
right here. Oh, look, a double bond is
Like,
forming.
he seemed to
And
get
the methyl group
where
is
the
shit.
action goes away.
Yeah.
Yeah, so that arrow.
He gave us all that. The government still shut down.
The oxygen.
The government still shut down. That's so sad.
And, well, I have 5 bonds already, right?
I know, what's the longest?
One and a
Yeah, I've been watching.
You see here? Now that matches that. Yep. You kind of have to follow. So the hard thing is you don't have any of these
Yeah, I
intermediate
saw like
structures.
this huge. It's not crazy.
Yeah.
But for now, we will.
It's scary.
I feel so bad for so many people who've been like
Cause
planning to
anyone,
go
this stuff
internationally
follows us.
or whatever, or like how
Okay.
people really do like go somewhere and just
Here, the action's gone. This is picked up.
we're all gonna finish.
Yes.
Is there flights for you?
There you go.
Is that like,
Right.
Yeah.
oh, like the
And
trans?
then
Yeah,
this
but
is
they-
on.
When we go there, they're not wanting me to take this.
It's closer you are to the date.
Yes.
Oh, yeah.
I guess, yeah, cause he.
Are you going home for Christmas?
I was there.
Yeah. Like Thanksgiving's like, that's not long.
Yeah, I don't know for Thanksgiving break. It's only like Christmas and Sunday.
No,
Unless you finish this, you're
it's
pretty
so
much.
expensive, but
good.
geez.
Are you done with all like the STEM, main STEM pre-req classes?
I know, I saw the
I'm not doing my schedule for them, I'm hoping that they let me.
Did you take
My boyfriend was telling me he had a medical interview in Boston for med school and he was looking to
Oh, you
go
do?
to med school.
I still
And
love
he's Tyler Hill, like he likes to search or like likes to venture into the surrounding city. And he'll ask people like, where should I go? What's a good spot? Like, what do you
No,
recommend?
she's really
So he
good.
did,
She has like
went to
very
the boroughs and
policies
stuff.
of the work or
And
just maybe.
I don't know, he didn't remember.
You never called the boroughs?
That's what he called them, and he's like, they were just like these guys at park, like drinking,
Her name
and he
is
asked
Chris.
them like, hey, where's a good tourist spot to go? And they fucking beat him up.
Yeah, I sound about right.
And he said he went to his medical school interview like a black guy in a bus.
That's cool, so.
He's like, I was just asking.
What's
You don't follow your
And you get the fun classes.
But you guys don't get is that when you see certain people like outside the
Really?
you don't find them.
I think it's a California thing.
I was having a conversation with the sister, like, oh, you can use my brain state, not very. Some cities, yes, certain cities,
Yeah.
you would be.
It's challenging, but
Yeah, you would have been, like,
I do feel like East Coast people are like thick skinned. Like they were, we'll tell you
Yeah,
they're
like,
like,
yeah.
been like,
I'm,
they
I
don't do
could
it.
fly
Yeah.
next year,
It's
but
like,
I'm like,
we're,
honestly,
I don't know, I'm not
I've
gonna say we're like,
one more
but
year.
you guys are.
uh,
Yeah.
Or the next 2 months.
It's like another song I saw on
I
Instagram
would
post
take
being
it
like,
comprehensive, but I'm like,
the fucking,
let's
the
get
workday
4 years
starts on
here,
East
like,
Coast.
I feel calm.
Cause that's like, yeah, and our days
It's like,
are
I have some
East Coast,
people
they
that
start
are
with
like,
us. So for so long, we've gone through so much crazy.
They're scrambling to get
Like the 1800s.
I'll probably
In
take
the
the next
state,
year.
I was like, we went through
Once I
a
take
whole
my MCAT,
100,
I'll apply.
almost like 200 year history before you guys
MCAT,
were joined.
That's so crazy.
I
Yeah.
have friends that all
And the people
over.
who moved down there
Yeah,
couldn't
right now,
handle
I'm
the
not
East.
Tell me to see.
Yeah, you're like,
And I was like, yeah, I'd rather die and go into this other place than stay
That's
here.
like,
I didn't even know the story.
No
You just told me the
Yeah.
other day. I'm like, oh, Boston? Wow.
Like,
I did. I was like, she's so kind.
I feel like the-
Sweet. He's like, yeah, she probably has a rough side to her. I was
That's
like,
a great
she probably
semesters,
does.
six semesters tough for me. I'm like,
Yeah, I just immediately thought
I
of it. I was like,
you
that's
know,
so
like,
funny.
it'd be like 10,
Yeah, it's always
10
like-
weeks and then week 11 is fine.
And it's like trying to write letters as well, where it's trying to have to learn it all really fast, and nice to get to know them, but if you don't know them, they will give you another.
It's very like, you do it and then forget it, or this, like,
It's
you
like the
know.
last time.
I think semester's nice when you're working.
Or there was a fight around
Or
some
like,
time,
you know,
13 for sure.
But not many.
I honestly want to, I mean,
So that's like, it's like,
there's just, we're more confrontation.
I think all you see this quarter is
birth, like, big sense of, we're just reading so much of it, so
That's cultural impact. Did you grow up in culture shock?
no.
it's like the
we're
weather
very
is
miserable.
miserable, fucking.
I have family in Sacramento, like for a long time, so we'd always
Traffic
slide and
is
see.
miserable, and then like people will be like, let me ask the dumbest question, and I'm like, no.
I know.
Like
They're
someone,
expanding
if someone came up to
more.
me and I'm in the middle of my question, like, yo, where should I live? I'm like,
Yeah. Okay, that makes sense. Understandable.
it's like, I know
There, I
so
think
many
from
people
when I
that are
was
like
in
that.
undergrad,
Honestly,
when
the fact that you
when
were
I first started,
college,
I think in the next few
Yeah.
years, like thousands of
Daylight
people,
hours.
Yeah.
the
Yeah.
acceptance
They
rate
have
went
zero
down
fucks
because
to give because
or
the
the
popular rest of
like went up
Yeah.
a lot.
Yeah.
So
And
it's
you're like,
fewer
you're
thousand
feeling
students,
seems
I'm
like
I see
friendly,
people
and the
surprised.
next thing
It's like this.
a stranger's pulling you back into another
Yeah, I used to
road
work
for you just to leave, just to leave.
And it is.
So
I used to work at.
beat up.
Oh, really?
Like,
Were you a professor or?
No, no, I was a admin, worked in.
Cause I mean, you went to, you ended up going to school in Mexico, right on the border. And he was like, they were even that bad in Mexico,
So-
they were like crazy there.
Oh, I can see that, even if you go to.
We start to fight
you said
for
you're going to
everything. I
Sac
know.
City.
I remember when I was
So you
in
still
school,
live
we
in-
had like really bad snowstorms one year. And our days do that, and so in Southie, it's not bad. It's like, this kind of like, the stage area, just bad city.
No, Woodland is like
It's
right
like,
here.
you have all these stuff right area, spaces and whatnot, it's like, no, but it's like.
From where I live, it is, if I wanted to go to
There's
downtown.
so all the parking lots.
Yeah.
15
So when
minutes
it's in
pretty
snow,
much.
they go in the people,
Like I'm
put,
far,
like, markers, like chairs,
you know,
cones,
or
and
even go to
things.
downtown.
Microphones.
Or
Don't
Davis,
pick my
or
spot.
Woodland,
And I
or
remember
the exit,
hearing
it's
someone
also
kill someone else.
Okay.
So I'm like, this is not.
Oh my god.
Wait,
And
so
it
you
was
live.
fucking.
You know where the
I was like,
Panda
honestly, I got that.
Safeway is?
Yeah.
Because like this
Like,
is like fucking.
even campus,
We got
like,
shovels
when I used to drive from there,
get into that
like 12
parking
minutes.
spot.
Okay.
Like get to your car out, then you have to
Downtown
get
is
more
like-
so that you can
well,
get back into this
it's
one,
like-
and then you
well,
can
it's
get
like-
people into the fucking college.
Yeah, I
That's fine. I work to make that spot
Yeah.
available.
No,
Hell no. Do you know how hard it is to shovel out?
I used
No,
to
I've
live
seen
in
YouTube.
West.
No, I've seen
It will
YouTube
take
videos,
hours.
that's
I used
crazy.
to live over there when
Wait,
I was,
I think I
when
went
I
on a
was
picture
early
of
on
like,
in college.
when I was in school.
Then the last.
That's insane to
After
even think that, like,
My-
early, like, just to get your car.
Oh, we will be up in the middle of
I
the
know.
night, cause like my
I
parents
was
house had
supposed
like
to
porches and
go
wooden, so like the way the
back
snow
to
can
the
like
area, but I'm
get
like,
into the wood.
Yeah.
So we have to shovel all the porches, and then you have to
Right.
double like,
I
we also have to shovel pathways
I mean,
to like essential areas of your house, so like you can get your backyard, or if you need to get like your oil, like.
I mean, I would
We're doing
going back
that.
home with my family.
Yeah, we do
like,
that, man. I remember
But,
growing up as a kid, the
I'm
moment
like,
you
like, also
could
to
walk well enough,
stuff.
you're getting shovels, like, I would freaking like, my dad,
Like, how was
literally,
it?
I was I was like, so big.
Yeah, but it sounds from.
You did
better
your
start
training,
home, but
yeah.
literally though, like, for me, my dad, he like, he's like very like, sex
Also,
and
you get like calls
like,
and it's like telling you that.
he was very much like, my sister had to put like mow our lawn when I was like,
Yeah. It's even people putting out like books.
Yeah, yeah.
shoveling stuff here like now, all
Everyone.
everyone,
We need the whole
It's like
crew.
the
We
biggest-
just-
it's like the
literally,
biggest
they're like,
That's
I-
so
or like just someone.
crazy. That's such a difference from living in California.
I work for this publisher called She Writes Press.
Let's see if I got this picture. Yeah. Here it is. Yeah. So this is like
Oh,
my car before I started.
yeah.
Oh my god,
That's
she was
cool,
so
though.
tired. Isn't it fun?
It's
And I enjoyed it for a really long time, but I was ready to do something else.
Would you still do
And
it?
that's
So they need, like,
I know, that's all around her
Ah,
car.
you can't. And then if it's like if you
Yeah,
maybe
maybe.
so
That's
we're
what-
just because
and
they
then it's
don't
fine.
it
It's
starts
just like
to
right now,
out and it needs to be thick and heavy. Because if it's like food, that's why you do like
Yeah,
chili,
it's
or
just
like
really
because it stays there and it starts to melt. It's just raspberry.
And they probably have, like, deadline.
They do, yeah, it starts to melt and you're just
Like,
like,
especially for those people that they can just.
It's like your car once it's stuck, is that why too?
yeah, because it's also like, and if it freezes
So
later,
cool.
whatever,
yeah.
melts, it becomes ice.
What's
And it sticks to your car.
Yeah, that's
scary.
scary.
Like, I grew up having to do that all the fucking time. If I could do that,
Yeah, all
it's
over
like
her
my
room.
fucking squad. And then some other idiot was like, oh, should I live around here? I'm like, fuck off. Leave.
Yes.
Not here.
Yeah.
Which is nice.
Focus, you can focus on.
Right.
Because once
I
you get
have.
I remember one time, my sister was learning how to drink.
be on a full.
That's why I was like, oh my god,
It might be like-
my sister and
I don't know
I
how.
just had a drive during that time, and she was driver's ed. Yeah. I remember the driving instructor threatened to kill me just because he was like, hey, you know, I was like,
You might have to be part of like what research lab, things like that.
I want that experience. I think it'll be really
he's
cool.
like, just drive this back.
Would you, if they were doing the Oxford things now, would you do it?
Certain stuff. Yeah.
I know a lot of.
I remember
professors
sitting in the back seat with my
there,
sister for that.
I don't know what specific, you know, a lot of professors I think is some. Especially having the easy. So it's like such a, I don't know, how sex is research. I have friends that went through, but none of them research.
It's not, New York City shouldn't work, so like,
But yeah, it's
outside
all,
more,
this
this
is
is
all
all survive in New York City, but I did not
the,
survive living there full time, like
the bachelor's
like
degree
not
stuff,
done.
like the whole stuff, just to like.
I go there pretty
start.
far.
I feel like I have the tools I need to.
I crap, yeah. I'm about to stop me more about it.
That's terrifying.
Is that like masters or?
Yeah, I've never done it.
I'm moving both. New York City is where you're gonna have to die. That's greedy.
So, yeah. No, we too.
Like, not even San
Yeah.
Francisco, it's so
San
crowded.
Francisco is like homeless people, it's like, if you're with homeless people, you're just as crazy.
Yeah, especially if
They're
it's
like,
someone
oh,
who's
they're
like,
like,
oh,
I respect that. In New York City, it's like,
I know they
they'll
don't.
be fucking crazy, but whatever, right, is gonna win. Exactly.
Yeah, so I wouldn't have to worry about like what a lot of people have to worry about, the rats out here.
Yeah.
I know, we were thinking about like, okay, where do we wanna go? And like start flying to schools, and we're just like
Remember the
looking at the
strikes
map,
and
we're out of
stuff?
state.
Yeah, there's a
And
lot of them.
he just brought up Boston, I was like, I didn't even consider Boston.
There's certain places, they definitely like,
Oh, yeah.
I will say it will be a hard transition.
Yeah.
It's
They
easy
do
to
those-
move, it's not too bad transition from east to west, but west to east, especially like when you're just, more efficient. Because like, if you put people turning back here, it's worse.
That's right. I know.
Because the sunset's
I took
for-
Kim, like,
Right,
yeah.
And then you'll get, and then in early
Mike
June, our
did the
whole
lab,
fund, and it's like
did
20
like,
days.
there was a session, which was just a supplemental lecture.
Yeah, I
And
don't
it was
know.
like twice a week for like an hour. But it was
Just interesting, I mean,
coming in.
I've never ever
It was,
considered like
it was
going
kind of just like
anywhere
nothing.
past
Like,
like,
okay, well,
let's say
yeah.
Texas.
Texas, you're considering Texas?
Just because we both have
I know
like
some
great
people
family
don't
friends that
yeah.
live in
Right?
El Paso.
Not saying bad,
It's
but it's
such
not helpful.
Right.
I have no idea, but
Yeah, like this would be, this is weather in February in my hometown, it's like,
We don't have to go.
it was like,
Oh.
oh,
My.
-10,
my
but then it
team
feels
opened
like
it was crazy. It was one of my-
because the wind is so cold.
but you're frozen or you come outside.
I had to work during those times, I worked on the outside.
They're, yeah,
And then
they're,
like,
they're a lot higher.
Were you wearing like a
And actually, it's also a small process.
Yeah,
You know,
I had
that's
to like wear
the
like,
layer.
that was honestly, they like had it kind of all the time, but it was like, because it's like light temperatures, you have like last 3 layers of clothing, or even less than 30. Because like, especially when I was doing it, like I was like like getting super sweaty and then like still come down after that. It's just like,
Cause you're wet.
classes that week is where you have like, but I remember one time it was like I had an Arctic Cobra and then we had a pipe issue and then I think I got my homework to grab the grown stuff and then it fucking started to freeze on me.
Yeah.
I was like, I'm
No, I
covered
would.
in frozen bananas right now.
I'm not. I like that I went straight through. I like, you know.
I mean, I worked in a freezer.
But I
That's
can't-
not
I would just
close
not.
to.
What's worse is I had coworkers who would like literally work there, like they were buffed out really guys, and they were like, the fairs on our work, they were like, delivery
Same
trucks,
as
and they would deliver
the
like
lab,
ones we delivered to like
it's the same way.
food when I was in house. And they had to fucking.
Yeah, actually from the
I think
freezer,
It's
it
a-
was passing off warmer than it was outside.
Yeah.
And load up,
Yeah.
go into the freezer, load up like the trucks, and it's just going back and forth to the freezer, cold outside and warm.
And two, I think here. This is the head tea, I think for Oakland.
Oh, yeah.
Sorry, comment.
All right. Hope we have enough break. Let's get. All right. So. Here's the exercise for you. All right. Predict the major organic products of these reactions. All right, let's take 5 minutes to try these. All right, so you notice they may look similar, but they're not because you can't flip them. All right, so one is the cis isomer of 1-bromo, 2-ethyl cyclohexane, and another is the trans isomer. All right. So you want to draw all expected products, okay? If there's more than two, please, or if there's more than one, sorry, list the major, label to which one's major and which one's minor, okay?
Get back.
And remember everyone, Tuesday, no class, all right? If you need to meet, please email me and we'll do something on Zoom or something. Oh, you guys are at a party? I'm not. No. Okay. All right, but let me ask, does like everyone want an extension on homework?
Yeah.
Okay, I'll extend it through Tuesday.
Thank you so much.
Hey, what's up?
Sir Andrew, quick question. For the step you have 3, are you gonna put that like out?
Yeah, I will. I'll put it out by this week now.
Okay,
Yeah.
thank you.
Thanks for the reminder. So if we do it then. Do you guys get a structure for the first one? All right. What's the functional group that forms? Or like you have a product, right? What does it look like? All right. Good. So you're gonna have this group there, and then like that, right? So that's our major. Is there another product that can form? All right. What's the other product that can form?
Would the other one just be on one of the diagonals instead of the straight?
Okay. Which one do you mean?
Like above that.
Yeah, above it.
Here?
Yeah.
That?
With the other,
And the alpha group's here?
yeah.
Did anyone else this one? Get it?
I don't think it's on the lower diagonal one.
Okay. All right. So let's remember that the bromine and the hydrogen, they have to be one carbon apart. So they have to be adjacent to one carbon. So I think you want to draw this one right here. All right, and we can see this. We can actually see why this structure is if you draw some chairs. All right, so let's draw some chair forms. All right. My alpha group is right here. Then my bromine is right here. So right now, my hydrogens and the bromines that are possibly able to eliminate, they are not in the right conformation. They're all equatorial. So we're looking at these hydrogens here. and the hydrogen I showed on next to the bromine. Okay. Let me just erase this really quick so I can have more space to the right. So, well, I can't work in this chair structure, right? So what should I do to the chair? Yes, let's flip it. Okay, so now these hydrogens, they're going to come down and up here, up and down here. So we kind of track these two positions, right? This one goes right here. And then, where's the bromine going to be? Well, the bromine was at this end, so now it's right here. So we're going to draw the bromine coming upward. And then the ethyl group, it was on the end, so it's still going to be on the end, but like this now, okay? So now I have two potential hydrogens to eliminate right here. Both of these are able to be removed and form a double bond. So we get these two products here. All right, this double bond right here, which is this one, and this double bond right here, which is this one. Right there. All right, so I think it'll be helpful if you kind of drew out which hydrogens are trans to the bromine atom, and that will help you decide which alkenes can be formed. Instead of kind of going in blind and say, okay, there's two hydrogens over here, maybe I can remove one of them. Because in part B here, you'll see that only one hydrogen can be removed. All right, so how do we do for letter B? How many products did everyone get? Any? One product. Okay, I like some of that. So where does the double bond form? Is it in between the bromine, where the bromine was, and the ethyl, like the first example? No. All right. Like some of that. Okay. All right. So again, I would recommend you draw a chair. Doesn't matter which form it is in right now. Okay. Well, my bromine's pointing down, so let's make this the bromine. So that's pointing down, Br. And then the ethyl group is pointing upwards. Okay. Well, the hydrogens here are not in the right positions, so we got to draw a chair flip where the bromine is axial. So let's just flip the chair. All right, so now the bromine, it's down, so it's going to be in this position because we follow how to draw the chair. And the ethyl group has moved one over, so it's going to be right here. All right, but now we have to draw the hydrogens that are trans to the bromine. So let's draw one over here, and then I'm going to draw the rest of this H. So this is kind of in the back there, okay? And then here's the other possible hydrogen, but this hydrogen is pointing down. So which hydrogen is the only one available to be removed for elimination? All right, so remember all these positions, these hydrogens are too far away to form an alkene, right? So it's either, and there's only one other hydrogen that's pointing trans to the bromine, so it's going to be this one. So this one would eliminate here. So what happens here, this would form a, oops, sorry, we won't do that. Double bond right there, bromine leaves. And the product we get is primarily the only alkene that forms. And it's going to look like this. So it's being one carbon away from the ethyl group. So this is the only product that we'll see, only product formed. Like that. Okay, so these cyclohexanes are prime examples where you can't rotate the bonds. So the hydrogens are locked in their relative orientation, either pointing up or down, relative to how you look at it. All right, so are any questions on these two examples? So they look very similar, right? You might think you could draw two products, but unfortunately, if there's a cis versus trans relationship, the hydrogens might not be in the anti relationship to the bromine. So that's why we only see one product here. Okay. All right, now we're going to talk about how to form alkenes from alcohols. Then we will get into the fun stuff. How we transform alkenes to more useful things. Okay? So I'll make a note, like this is where the majority of the alkene reactions start, and that's a bulk of what the final exam might look like. Alkene type reactions. Okay? This upcoming exam, I might even talk about alkenes. I might just stop at ethers, alcohols, and synthesizing an alcohol from a starting material. So that worksheet, I handed out last week. Try to attempt those. I'm going to post the key, okay? You can expect one type of synthesis type problems. Probably worth less than 10 points, okay? All right, so anyway, let's talk about alcohol preparation. So preparation of alcohols. Preparation of alkenes is what I'm talking about. All right. So first we have reaction of alcohols with strong non-nucleophilic acids. All right, so these acids are usually phosphoric acid or sulfuric acid. You can't use nitric acid. Nitric acid is too strong. So phosphoric acid, H3PO4, 140 degrees Celsius. Okay. All right. So how many products do you think we'll have here? All right, so let's think. Is this alcohol symmetrical? Yes. So you might think there's two alkenes, but it's the same thing wherever you draw the alkene. So it's going to be just one product. All right, so this is how you form cyclohexene. All right, so let's go over the mechanism. Might be good practice for today. So we're doing this type of reaction in the lab too. Maybe dehydrating alcohol, partially. All right, so what's the first step? Good, yeah, protonation. Okay. So we protonate the alcohol, make it a better leaving group. So now we get out dihydrogen phosphate as our counter ion here. Good. So since this is a secondary or tertiary alcohol, always kind of assume carbocation formation first. So we now go to a carbocation. And then how does the carbocation get kind of quenched or consumed? Say again? Oh, close. So it's not a hydride shift because if we do a hydrogen shift, it'll just get the same carbocation. So we're just going to remove the hydrogen with water. And that will produce the alkene right here. Here we go. So the final products here are cyclohexene and H2O. All right. Well, sorry, not H2O. The acid gets regenerated because it's acid catalyzed, so H3O plus. All right, but the carbocation rearrangement is coming up. So that's our next example. Okay. So now, pay attention to this one. There might be a reason why I'm telling you to do that. Okay, so what about if we have an unsubstituted alcohol and have a position, more substitute, we have a asymmetrically substituted alcohol. So both sides of the alcohol are not the same substitution pattern. You might have what we call rearrangement, right? All right, so this is where rearrangements happens and during the E1 mechanism. So the major product of an E1 reaction is the more substituted alkene. So when we have alcohols and alkenes, the more substituted product will be the major one. Okay. So let's say we have this one, OH. All right. So same conditions: phosphoric acid or sulfuric acid, doesn't matter. All right. So what kind of alkene would you form here? There's two ways we can form an alkene, right? To the left of the OH and to the right. Which one would be the major? Yeah, so the tetra or tri-substituted alkene will be the predominant product. Like that. Okay. Okay. And then the problem with these reactions is that you'll have carbocation rearrangement. So that's totally possible too. So carbocation rearrangement. All right, so say you have this product, this starting material, and you get H3 phosphoric acid again, under 40 degrees Celsius. But your product is a little weird. It's not what you expect. You actually get this alkene as the major. How can we explain that? All right. Well, looks like a carbocation is forming, so we kind of have to maybe shift the carbocation a bit. All right. So let's go through the mechanism once again. As always, what is the first step? Yes. So you're going to protonate the alcohol from the acid, right? Okay. So plus H PO3H2. All right, boom, boom. All right, so this will give you the same steps we saw with the other example. But now we have the carbocation. Okay, so what's the next step here? Well, I can't just form the alkene right away because it'll be in the wrong positions, right? It won't be next to the methyl group. So what happens first? Yes, so water now leaves to form a much more powerful electrophile. So we get this carbocation. Okay. Now, the alkene is still too far away from forming. So one thing you can get from this is that carbocation rearrangements, they're always in equilibrium. So they can occur if you have a similarly stable carbocation forming or a more stable carbocation forming. So if we move this hydrogen over here, what kind of carbocation do we form? Still a secondary, but we're going from a secondary to secondary, so that's still thermodynamically okay. So that's still a favorable thing to occur. Good. So we do that. We now draw the result of this hydride shift. So now the hydrogen has come right here, a new hydrogen, and the plus charge has gone over here. So now you can kind of think, oh wait, couldn't we just do another carbocation shift? Yes, you could, but that won't affect the product, how you form the product, so you don't need to, okay? So what's the last step here to form the alkene?
The water, take the hydrogen, and the carbon with the methyl, and the bond from the hydrogen goes back into the carbon-carbon bond.
Yes. So water here is acting as our base, do an E1 reaction, and now you form the double bond right there. So now you have acid regenerated, and your alkene here will form right there. And notice, it doesn't matter if we go from that hydrogen. Well, let me backtrack there. So that's how that product forms. You can also form the same product if you did another carbocation shift to the tertiary position, but don't worry about that. It's fine. Okay, so that's our how to make alkenes. So we take something with a good leaving group and then do elimination type reactions with it. Okay? Yeah, Catherine.
You mentioned this previously with alcohols where it was like with a carbocation, but even though like we're only doing a carbocation from a secondary to another secondary, is that only allowed with alkenes or
No. So it's with any reaction that generates a carbocation. So like SN1 with a halogen on it, you can still do it too. Yeah. Yeah. So it just has to do with the intermediate. It's not influenced by what product you make. Yeah. All right. Well, we got a few minutes, so let's just start this. So reactions of alkenes now. So let me put a star by this because this is beginning our long list of reactions for alkenes. All right. Number 1, hydrogenation. All right, so this introduces first few reactions of alkenes where it's stereospecific. All right, so only it adds in a specific way. So we have here a stereospecific reaction. All right, does anyone like margarine spread, like those butter type things? Well, hydrogenation is how you make it. Usually, things are very oily, okay? But you hydrogenate some of these bonds, it makes it more fatty, and it makes it more solid in structure. And that's what the food industry does for margarine. That's how they make it from food fats, okay? So here we have are alkene. All right, so the typical conditions for hydrogenation is you have hydrogen gas and some type of catalyst. Right here, the catalyst is usually platinum or palladium. Right now, I just did Adam's catalyst, platinum oxide. And the solvent is usually something polar, acetic acid, or an alcohol. And 25 degrees should do the trick. And you would do this reaction under pressure, so it'll go faster, okay? So here what we get is two products because remember alkene is planar, so you're going to get both enantiomers. So you're going to get the hydrogen adding from the top face and the hydrogen adding from the bottom face. Oops, sorry. Let's go back. All right, plus the hydrogen now is adding from the bottom face. Okay, so here you have 82% total yield of both enantiomers. So this is cis 1-ethyl 2-methyl cyclohexane. And it's a racemic mixture. Okay, so you started with 1-ethyl 2-methyl, and cycle, what's it called now? Cycle what? Close, hexene, it's 6. All right, so the other catalysts you could use here are palladium. So other catalysts are palladium on carbon, the one I showed at the start of this class. All right. All right, the mechanism is very specific, so I'll go over the mechanism on next Thursday, not Tuesday. No class on Tuesday, okay? All right, so that's it for today. And we'll meet back in lab in 10 minutes, okay? And get there early. I'll check their pre-lab so you can kind of get started as the lab starts. Thank you. And guys, before the next exam, I'll create a list of reactions you should know so it's easier to study, okay?